Thanks everyone for coming to hear me speak. The goal of this presentation is to kind of give a conceptual overview of some of the concepts of machine learning, in particular what we call predictive modeling. And in my experience, you know, there's a lot of jargon out there. There's a lot of mumbo jumbo. There aren't a lot of really clear explanations that actually make the concepts accessible. And so that's my goal with this presentation. I'm going to start with sort of an overview of, you know, what do we mean when we say predictive modeling? And then I'm going to give a brief demo using the BigML tool on an actual data set. Okay. So what do we mean when we say machine learning? I'd say the short answer is finding patterns in data. And so, for example, there's the famous iris data set, which has measurements for 150 flowers, 50 of 3 different species. And you've got the 3 species up here. And what we're trying to do is predict a flower's species using its measurements. And so this is what the measurements look like. You can see we've got petal length on the horizontal axis. We've got petal width here on the vertical axis. And the red dots represent one species. This is another species. This is another species. And so we have this data, and kind of looking at it, you can see that there's a pattern here, right? The red is all in this corner, the blue is all in this corner, the green is sort of in the middle. So, you know, this species here has long petals and wide petals. Over here, this species has short, fat petals. And just visually looking at this, you can see that there's a pattern here. But what we're going to do is we're going to play a game where we're allowed to draw lines between the dots. And we're trying to draw lines so that you get a pure concentration of dots on one side of the line or the other. And the restriction is that we have to use straight lines. We can only use horizontal lines or vertical lines. We can't use diagonal lines. That's the way we're going to play this particular game. And so if I show you this, and I ask you to draw a line, it has to be vertical or horizontal. And the goal is to create a pure region on one side of the line that's purely a single color. Where would you draw the line? Well, if you look at this, you could draw the line there, or you could draw the line here. And if you actually feed this data into the BigML algorithm, that's where BigML will draw the line. BigML actually looks at this data and it says, it figures out, using the algorithm, that this line is going to give you this very pure group of dots over here, right? In this rectangle, there's only red dots. Okay, so I'm done over here. Now I have this rectangle that has 2 different colors of dots. And again, I get to draw one line, and it has to be either vertical or horizontal. So what line am I going to draw? Well, that's the line that BigML is actually going to draw. And again, you can see that we've got, you know, now we have a pure collection of blue dots over here. All right, so far so good. So this rectangle is all red, so we're done with that. This rectangle is all blue, so we're done with that. Now we have this rectangle in the middle, and the line that BigML draws is here. Now, interestingly enough, you can see that this is not a perfect separation between the blue and the green, but it's the best that we can do, right? This rectangle here contains mostly green dots with one blue. This rectangle over here contains mostly blue dots with a couple of green. And we're going to stop there. You could keep drawing rectangles, right, until each data point had its own rectangle, right? At some point, you have to stop. And so we're going to stop here. Well, congratulations. We just trained a model. And these rectangles that we just drew can be used to make predictions about flowers that we haven't seen before, where we don't know what the species is, just by looking at the length and the width of their petals. So if I see a dot with short, fat petals, I predict, based on the model that I created, that it's going to be Iris setosa. And same thing for if I have a flower that falls in this green rectangle over here, I'm going to predict that it's Iris versicolor, and so on and so forth. Now, we're going to be a little bit less confident in this prediction because it's only based on a few data points, and it wasn't a perfect, it wasn't all one color in the square, right? And that's an important concept. How much confidence do you have in your prediction? Which is another way of saying, how real do you think this rectangle really is in representing the reality of the data? But the key concept here is that these rectangles literally are the model. It is completely correct to say that this collection of rectangles is the model. The model is this group of rectangles. And so when people talk about predictive modeling in the abstract, I always think of rectangles, right? I always think of this particular approach where we're taking our data and we're drawing these rectangles, trying to separate the two classes, trying to create rectangles that contain only a single color of data point. And so I think this is a nice concrete way to think about the concept of predictive modeling. You're drawing these rectangles. Those rectangles are the model. So you'll notice that, and by the way, this process is called scoring. So when we actually take a previously unseen data point and figure out which rectangle it belongs to, that process is called scoring. And so, and by the way, you can actually try out the Iris data set at BigML, and it will tell you what predictions it's making for which little rectangle. Okay, so what? Who cares? The point is that that process has two steps. The first step is drawing the rectangles, and the second step is figuring out which rectangle a data point falls into. And so the process had two steps: training, drawing the rectangles, and then scoring, which is figuring out which rectangle a data point falls into. And if you think about it, when you're training on historical data, you're often looking for patterns that emerge over weeks, months, even years. But when you're scoring a new data point, right, when you're taking that flower and you don't know what species it is, and you figure out what rectangle it falls into, well, you want that to happen instantaneously, right? You want to get the answer, you want to get the prediction in real time. And so this raises the question, we've all heard about real-time analytics, real-time machine learning, whatever it is. I personally wonder if real-time machine learning is even really necessary or useful in a lot of cases. You think about the large amount of historical data that you need to draw these rectangles. You think about applications like credit scoring, fraud detection, movie ratings, et cetera, et cetera. An extreme example is text recognition, where the alphabet doesn't change at all over time. You might be adding fresh training data to your data set, so you can draw better rectangles, right? But you're still going to have a lot of historical data when you're training your model, when you're drawing those rectangles. And so, again, you definitely want to score in real time. Once you've drawn the rectangles, you definitely want to know instantly which rectangle a data point falls into. That you want to have happen immediately. And so this kind of sums up the idea here. You know, there is not a major shift in the media landscape every 6 seconds. And that's kind of the idea here. You're building up a training set over time so you can draw the best rectangles you can for whatever you're trying to predict. And so the next time you hear someone talk about real-time machine learning, you can make yourself look really smart and ask if they mean training, drawing the rectangles, or scoring, figuring out where a data point falls in a rectangle. And then see what reaction you get. Okay. This is good. This went over much better than in the United States, actually. I think there's a lot more European Monty Python watchers, so that's good. Next, I'm going to go through a brief demo using BigML on an actual data set. This is a data set from a web application called StumbleUpon. It's an app that recommends web pages. This training set has 7,400 web pages, and each one is labeled as evergreen or ephemeral. And evergreen means of continual interest. Ephemeral means of only passing interest. And here is the data set in BigML. So you can think of this as a text file with about 7,400 rows in it. Each row is a web page. So the actual unstructured text of the web page is actually in this data set. It's a field called boilerplate. And there's a bunch of other stuff for each web page. There's the web page's URL, its category, and a bunch of other different stuff. There's like 25 different fields here. You know, does it have, how many spelling errors does it have, and you know, how many images does it have, and all these different attributes of each of these 7,400 web pages. And the thing we're trying to predict is this thing called label. And label is either a 0 or a 1. 0 means that it's ephemeral, right, of only passing interest. You know, an example might be a news article or a blog post that goes stale very quickly. And category 1 means that it's evergreen, which means that it's something of continual interest. And an example might be a recipe website. You know, the recipe is going to be useful today, tomorrow, a year from now. And so I've already taken the step of loading this data set into BigML. And I'm just going to do one-click model. And when I click this, BigML is going to draw those rectangles, very similar to what I showed earlier in the presentation, only instead of having 2 axes, the data has 25 axes, or 26 axes. BigML is actually going to be drawing hyper-rectangles in this 26-dimensional space. But conceptually, it's the exact same thing that we saw with the flower data set. So one-click model. And by the way, this is all happening in the Amazon cloud, so it's very fast. One of the nice things about the BigML approach is that you're not limited to the compute resources of your laptop, for instance. And there's also nothing to install. And so here we go. Now, the way to read this, and again, think back to that example we had with the flowers, right? We start with 100% of the data set, and that data set contains roughly 50% class 0 and 50% class 1, which is evergreen. And the algorithm goes through and it says, okay, I get to draw one line. The line has to be parallel to one of the axes. and I only get to pick one thing to split on, to divide my data into two rectangles where we have as many class 1s on one side and as many class 0s as the other. Right? We're trying to draw these boundaries and create subgroups of web pages that are either purely class 1 or purely class 0. And so the first thing the algorithm figures out is that if the free text of the website contains the word recipe, then wow, almost 90% of the time, that's going to be class 1. Right? And you can see that distribution here. In this subgroup, the subgroup that where the free text of the web page contains the word recipe, it's mostly class 1, which is evergreen, right? Something that's of continual interest. And that's a real contrast, right? Compare that to the original data set, right, where it's 50-50. Well, here we figured out how to create a subgroup of that data set that's almost 90-10 of one particular class. Now, the flip side of that is the subgroup that doesn't contain the word recipe. And so you can see here that this is a subgroup that has more zeros in it, right? And again, contrast this with the original group, which was 50-50. So the algorithm is making good progress getting this separation between the two classes. And so it keeps splitting, right? It keeps splitting the data into smaller and smaller rectangles with the goal of creating rectangles that are either purely one class or purely the other class. And in the process, it finds some pretty interesting patterns, right? If the text doesn't contain recipe or food or baking, if it isn't the health category, if it doesn't contain the word flavor or the word slice, right? If it doesn't contain all of these words indicating that the web page is a recipe site, right? Then we're strongly confident that it's going to be class 0. And by the way, Big ML doesn't know anything about the semantics of the text, right? It's simply finding these patterns in the text. It figures out that just looking at the data, that if the text of a web page doesn't contain recipe, food, baking, flavor, or slice, that it's probably not a recipe website. In this particular data set, that means it's probably not evergreen. It's probably not of continuing interest. And by the way, this is kind of a quirk of this data set, that recipe words matter so much. But that's what StumbleUpon put out there, and that's the patterns that, that Big ML was able to find. So you'll notice that I'm kind of hunting around for these patterns, right? This visualization is good, but there's an easier way to see what the patterns are. We call this the Sunburst. And it can take a little getting used to, but the way to look at it is that 100% of the data points are here in the middle. And you can see that, again, it's about a 50-50 split between the two classes. And these arcs that are sort of radiating out from the center, the length of these arcs represents how many of the web pages actually fall into a subgroup. And so you can see that there's this subgroup that contains, roughly a third of the data. Now, this coloring, this green to brown shading, basically brighter green means you have a more pure separation between the two classes. Either a high concentration of class 0 or a high concentration of class 1. And so the nice thing about this visualization is that without even knowing anything about the data, you can just look at it and you can see, oh, there's this big bright green thing over here. What's that all about? And you can immediately see that, oh, okay, about a third of the data is very strongly class 1. That's the group where the free text of the web page contains the word recipe. And so you don't have to hunt around in the decision tree to find the interesting patterns. You can actually just look at this visualization. It will immediately tell you, hey, look over here. And you can go further down and you can see that you get a more pure separation. You get a more pure subgroup if the text contains the words recipe and the word salt, and does not contain the word diet, and so on and so forth. So that's great. Now I've trained a model, right? I've drawn these rectangles. That's what this is all a representation of, these rectangles that enclose different data points. How do I know how accurate this model is? Because I can draw any set of rectangles I want, right? That doesn't mean that it's going to be correct. That doesn't mean it's going to correspond to reality. And so I can actually go back to my original data set, and what I'm going to do is I'm going to click one-click training and test. And what this is going to do, it's going to peel off 20% of the web pages. It's going to hold those out, and it's going to keep those from the algorithm. I'm going to train I'm going to train a model. I'm going to draw those rectangles on the other 80%. But I'm going to hide the 20% holdout set from the algorithm. So I click this button, and what's going on here is BigML is separating the data into these two groups. We call them training and test. And then it brings up the training set for me. And so you can see this is 5,900, 80% of 7,400. Otherwise, it's the exact same data set. And so I'm just going to do the same thing I did before, which is create a model. Again, we're trying to predict class 0 or class 1. Again, this is all happening in the Amazon cloud. And we are, again, we're creating these rectangles, these hyper rectangles, and we have this model. It's finding pretty much the same pattern, right? Even though it's only on 80% of the data set. And I'm going to do evaluate. And so what this does, we're going to score the 20% holdout set on the model we trained using the 80% training set. And if you remember when I defined scoring before, right, you're taking a data point that you haven't seen before. You're putting it, and you're figuring out which rectangle it falls into. And then you're making a prediction based on that rectangle, right? That's exactly what we're doing here. So I'm going to click evaluate. And now BigML is taking all those data points in the 20%, which the model doesn't know about because we hid those data points. And it's telling us that about 72% of the time, the rectangle makes a correct prediction, right? We're able to take a data point, put it in a rectangle, and get the right answer, whether it's class 0 or class 1. And I can see that that's better than random guessing, right? Random guessing is going to get you about a 50-50 chance of getting the right answer. But you know, I want to do better than just 72% accuracy. So I'm going to go back to my data set. I'm going to go back to my 80% training set. And instead of training a model, I'm going to train an ensemble. And an ensemble is basically a number of decision trees. In this case, it defaults to 10 decision trees. Each one of these decision trees is trained on a subset of this data, of this 80% of the data. And then we have the trees vote on what they think the class is. And there's sort of very deep statistical reasons that this works, but you can kind of think of it like having a bunch of people in a room. They each have different knowledge about the problem. They're each voting, and the voting process sort of captures the aggregate of their knowledge, which is better than just relying on one vote. And so I click this button. BigML is now training an ensemble of 10 decision trees. And by the way, that's what we call this algorithm, is a decision tree algorithm, where you're breaking the data into these subgroups and drawing these rectangles. And so BigML is training these 10 trees, and you can see it happens somewhat faster than training a single tree. It looks like it's doing it 2 trees at a time. And again, this is one of the nice things about doing this in the cloud. You know, we have a whole cluster in the Amazon cloud that can actually train these models in parallel, and you're not restricted to just the compute resources of your laptop, for example. Okay. So it's done calculating, and it's bringing up the model. And you can see that we now have 10 of these models here. And I can click through to these if I want, but I'm really interested in how accurate this ensemble is, how accurate this model of models is. So I'm going to do the evaluation again. And it's the same as last time. I'm scoring this 20% on a model that I trained on the other 80%. Click Evaluate. And now it's going to tell me how accurate this model is. It's scoring all those data points. And hey, we're almost 77% accurate, right? I didn't do anything differently. I used the exact same data set. Simply by using 10 models instead of 1, I was able to get a more accurate predictor. And so that's one of the cool things about ensembles is that it's like, it's almost for free. You get this increase in accuracy. You don't have to do anything different to your data. You don't even really have to do anything different to your algorithm. You just have to use the algorithm several times and have all the different trees vote on what they think the class is. And so the key concepts just now, number one, BigML automatically figured out these patterns in the text, right? We call that bag of words text analysis. Basically looking at, you know, how many times does the word recipe occur? How many times does the word salt occur? And even without knowing anything about the meaning of the text, BigML is still able to find these very nuanced patterns, right? If it doesn't contain the words, you know, recipe, salt, food, whatever, then it's probably a class 0. I showed how we evaluate the models using holdout sets. I did that first evaluation we saw was about 72% accurate. And then combining multiple models, we saw that that boosted the accuracy to about 77%. Again, simply by using a collection of models on Ensemble and having them vote on what they think the class is for each web page. One final thought. None of this data was big, right? The Iris data set was 150 rows. The StumbleUpon data set was 7,400 rows, each row representing a web page. And it was only 21 megabytes. And so, despite all the hype around big data, I hope I've demonstrated that data doesn't have to be big to be useful. Thanks very much. I'll take some questions. Yes. Yes, go ahead.
Okay, so this tool is very nice and easy to use, but what kind of level of statistical expertise would you say is the minimum?
What kind of level of statistical expertise would you need to actually use a tool like this? So this tool is designed for the power analyst, or at least the web interface is designed for the power analyst. You know, we also have an API you can use if you're more technical. But you know, you think about you think about companies, you think about the analysts at those companies, you know, you have a bunch of people who maybe aren't data scientists, but they're still writing SQL queries on the database. You know, they're playing with the data in tools like Excel or Tableau. They're doing a bunch of analysis. So you need a little bit of understanding of the concepts to use this tool. You don't need to be a PhD in, you know, machine learning. You just need to be able to put together a training set that you can hand to BigML so it can draw those rectangles. That's a great question. Yes, in the back.
Can you configure the system to avoid overfitting? I mean, can you tell the system to stop splitting the nodes?
Yes.
You don't have information gate, either that.
That's a great question. So just to repeat the question, how do you prevent BigML from overfitting the data, right? From drawing rectangles that are just memorizing the training set. Well, so one way to guard against overfitting is through the evaluation that I just did, right? If your rectangles don't mean anything, then you know, that's going to show up when you do the evaluation. It's going to show up as having bad accuracy, right? It's also pretty easy to do cross-validation using the BigML API. And so that's one defense against bad models. Another defense is what we call statistical pruning. And so this is kind of a general overview, so I didn't really get into that, but if you remember way back here, I said that we're going to stop drawing. Oh. Oh, they're, oh, okay. I said we're going to stop drawing, right? This was the last line that we drew, right? Well, how do we make that decision that that's the last line, right? Why don't we keep going and keep subdividing it into smaller and smaller groups? And the answer is we do statistical tests to see if, you know, if we really think we're getting information, right, a meaningful increase in the purity of the rectangles when we're drawing another line. And so, yes, we use statistical pruning to manage the complexity of the model. You had a question in the front?
Can you handle dimensions that change over time? For example, data traffic and so on?
Can we handle dimensions that change over time? So, you can create columns in your data set that are time-based, right? You can have a column that's like number of purchases in the last 6 months, for example. And very often that will get you there. Right now, we don't explicitly handle time series data. There's another question in the middle somewhere. No? All right. Well, thanks very much. Oh, go ahead. One more over there. Okay.
Yeah. Which algorithm has been implemented in that framework? Which machine learning algorithm has been implemented?
Okay. Yes. Which algorithm? So this. They're going to start playing the music, and I'm going to like get swept off stage here. Thank you. So this drawing of the rectangles, this is a decision tree algorithm, right? When you're separating the data into recursive subsets. And when you take a bunch of those and put them in Ensemble, that's called a random forest. And so for predictive modeling, those are the algorithms that BigML uses, decision trees and random forests. Great questions. This is like a really technical audience. I hope, you know, it said general introduction. I just want to be totally clear about that. So. Thank you very much. Thank you.